Okay, great. So that should be started.
Hey, I guess I should introduce myself as well. So I'm Ollie. I'm a PhD student, second year PhD student in the maths department, where I'm in the quantum information group, and I sort of work on a mixture of stuff from thermodynamic mapping schemes to quantum metropolis. And over the summer, I went for a 4-month internship at Riverlane, and this presentation is about the work that I did there. Here's the link to the archive posting if you want to have a look afterwards. But effectively, we were trying to. Christoph's in the house, my supervisor, and he's a lovely guy and very, very smart and was brilliant to work with. So anyway, what we were trying to solve, or the problem we were working on, is the data loading problem. So how you can load an arbitrary state into a quantum computer, which is potentially a bottleneck for a whole load of algorithms. Because if I wanted to prepare, if I want to prepare a arbitrary state exactly, then there could be 2 to the n pieces of information that I need to put in, and so unavoidably I'm going to need 2 to the n rotation gates. Now that's very costly and is essentially a bottleneck. So there's some stuff we can do to get around this. I keep walking into the projector. It's like I put the laptop over here. Okay. There's some stuff we can do to get around this. We can think of some sort of classical compression technique whereby instead of exactly loading 2 to the n states, we load some sort of approximation to them. And there's a bunch of different ways of doing this. I'm going to focus in particular on doing this with a polynomial approximation. So if I have a state where the amplitudes can be efficiently approximated by a polynomial, then a low degree polynomial, then I can efficiently load this onto my quantum computer. Now, this was originally done by Mercado, Gillian, and Berta, where they developed a technique that we very much built upon. And what we do is we extend their approach of using QSVT to load a low degree polynomial onto a quantum computer. So the process sort of looks a bit like this. If you look on the far left, you have the exact state that you want to load. Now this has a bunch of different amplitudes, and we can go, hey, this looks suspiciously like x squared, and that's has a lot less information. That's a high compression. And then we can use quantum singular value transformation to sample our amplitudes uniformly from a given polynomial. So then we can go from the polynomial we've used to approximate amplitudes, load that onto the computer with equispace samples, and then we get this state on a quantum computer, which is an approximation of our original state. And so that's the process we go through. First, I'll talk about how they originally did this QSVT, taking a polynomial and producing equispaced amplitude samples. Then I'll talk about how we've extended this by, instead of just doing a single polynomial, you might have a set of amplitudes that are well approximated by a piecewise polynomial. And that's how we extend it. And then I'll explain how that algorithm works. And then I'll go on to explain why you might want to use piecewise polynomials. So what cases is a piecewise polynomial going to give you a better performance than a single polynomial?
Can I ask a question at this point? This feels very one-dimensional in terms of the way you're presenting it. Yeah. Is it? Or if I wanted to represent, most wave functions, they're happily nice and smooth and continuous, maybe in 3 dimensions. But if I try to create a linear mapping onto 1D, that doesn't always work.
So this was exactly the inspiration originally behind the project, was that if I have a nice 2-dimensional, say, grid that's all smooth, but then I put it in 1D, suddenly have these discontinuities. And so we were like, oh, well, if I have a piecewise polynomial, I can now approximate each of these sections efficiently. And that was exactly the original inspiration behind it. Though as we went on, we found other sort of more provable performance boosts, if that makes sense, which are the ones I'll talk about. So first, I'll just quickly give the background on what the quantum singular transform is and how it works. So it builds on this concept of quantum signal processing, which is a result from linear algebra, effectively, whereby if I have 2 matrices, one of which, the S matrix, is parameterized by some phase factors phi, and I multiply them in order. So in a quantum computer, this is, we'd be applying this to a single qubit, and it's going to look something like I apply U, then, well, actually, the first one I apply is S with some phi 0, then I apply U, then I apply S with some phi 1, and so on and so forth. You can prove that this will give you in the top left of the resulting matrix that this gives you. You'll prove it gives you a polynomial transformation of the top left entry of U. So what this top left entry really means is if I have my U here and I start in the 0 state, and then when I measure, I get the 0 state, I will just get A. And you can quite quickly see that this is what's going to happen in the forwards direction, at least. It's harder to prove the reverse, but in the forwards direction, so if I start with, you know, U, which is A, let's say squared, let's say, is this showing up okay online? And then I have my S.
Yeah, sure.
And then my U again. When I multiply these all together, the top left entry, you can see is going to become something like A squared e to the I phi plus e to the minus I phi 1 minus A squared. So that's, and then the other entries will be some, there'll be some junk we don't necessarily care about. What we care about is what's happening in this top left entry. So now, the change that happens when you go to the quantum singular value transformation is instead of encoding a single A, what we do is we encode a whole matrix A, capital A. And in this picture, what that means is that now instead of having a single qubit, we have a unitary U that acts on flag qubits and block qubits. And on the flag qubits, we want them all to start in the state 0, and then when we measure them, we get the state 0 on all of them. And then the action of this on the block qubits will be the matrix A. And so that's what we mean by a block encoded matrix. And that's the definition we'll be using to prove that the block encoded matrices we use later on actually give us the matrix that we want. And then when I apply a similar process, so now I have to sort of also change my definition of S, because I no longer want to do a rotation on a single qubit, but a rotation on a sort of qubitized space, like a projective rotation where I apply one phase when all the flag qubits are 0, and I apply a different phase when they're not all 0. And you can think quite simply about how to do this. So if these are my flag qubits, then I can condition on them all being 0. So this control here is them all being 0, act on some ancilla with just a C0 gate, then apply a phase here, just an RZ of phi, and then undo just so it's reversible. And then this is the new S, but it means we have to add this additional flag qubit into our system, and this is the QSVT flag qubit that we're referred to. So you can see that on the next slide as sort of how it looks. Instead of our SU, we now have our new S slotted in between each U, and we have this additional flag qubit that's been added in. But still, if all the flag qubits start in the 0 state, and when we measure them, we get the 0 state, what we'll have acted on this X line with is a polynomial transformation of A. Now, by polynomial transformation, what I mean is, so A doesn't have to be square, it will be some maybe, but it has to be definite parity. It'll be something like this, sort of just the equivalent. And one of the easiest ways to think of this is if I take A and I do the SVD decomposition, so singular value decomposition of it, then the polynomial just applies a polynomial transformation onto each singular value of A. And that's the definition that we'll be using most throughout the rest of it. Just the talk. There's a couple of things to bear in mind, some caveats here. One is that you can't approximate any polynomial with this technique. I can only approximate polynomials where P is definite parity, which is because otherwise, if they're not the same size, A plus a dagger won't be not an operation like before. And more importantly, P of X it has to have magnitude less than 1 in the range -1, and on the domain -1 to 1. That should be a
Just that, so it's block code.
yeah. It's because when we do this polynomial transformation of the singular values, they have to still lie between -1 and 1.
What does definite parity mean?
Definite parity means that it either has to only be an odd polynomial, so only x plus x cubed plus x plus 5, or x squared plus x, etc. Though we do relax this constraint. You can relax this constraint by adding in a further additional qubit and controlling off it, or there's a couple of different ways of doing it. In fact, the later circuit I'll show, we relax this constraint. But then the other cool thing about the quantum singular value transformation is that these phase factors uniquely describe the polynomial. So once I have figured out the phase factors that I want to use to generate a given polynomial, I can substitute in any block encoding into my circuit, and it will do a polynomial transformation of the singular values of the new block encoding. So it's sort of plug and play in that respect, and we can use the results from quantum signal processing to figure out the phase factors. We don't have to do any new maths there effectively, which is what makes it quite powerful. So this very simple circuit can sort of do almost arbitrary quantum stuff. In fact, the paper, the grand generalization of quantum algorithms, where they demonstrate how you can approximate a whole bunch of quantum algorithms just using this technique with particular polynomial approximations.
So fine, so those angles effectively. How much choice do you have in the granularity of them? Because an arbitrary rotation angle it can be quite painful if you need it to be.
No, exactly. So there's a payoff in the cost, and there is ongoing research into the robustness of these polynomials. Though from a sort of back of the envelope style approach, you can sort of see if I have a epsilon error in each angle, I'm sort of going to get an additive error at the end in terms of my amplitude. So you can bound that. But there is some numerical instability in calculating them depending on which approach you use, so that can cause problems as well. So that's how QSVT works. So if I didn't explain it very well, the only thing that you need to remember is this top line, that it's a process where you transform the singular values of a block encoding by a given polynomial specified by the phase factors. And then once we have that, we can go ahead with the approach that the McArdle paper took, which is we want to take equispace samples from our polynomial. So what we want is the singular values of our matrix to be equispaced. And in particular, it's easiest just to take a diagonal equispaced block encoded matrix. So here we have the matrix that goes from 1 minus 2 over n all the way down to -1 plus 2 over n. And then I do the polynomial transformation of the singular values, which are just the diagonal values, and I get the matrix on the right. And now I can apply this matrix, which would just be P of all of these, to the uniform superposition. So as mentioned about this, the uniform superposition will look something like 1, 1, 1, 1, 1, 0 down here. When I apply it, I would just get the sum of P of 1 minus 2x over n. Quite importantly, with this zeros in the flag qubits plus some junk. And then it's necessary to do either you just measure until you measure the junk being all 0, or you can do amplitude amplification to amplify yourself onto the state where the junk is all 0. Yeah, so that's the approach that they used. And that's how you can sort of take up, you can do this second step here. So does anyone have any questions about that approach before I move on to? Okay, so what we have now is our extension of this, which is this idea of if you have a set of amplitudes that isn't fitted by, well approximated by a single polynomial, but is by piecewise polynomials. So you see on the left, I can fit this with 2 polynomials, and then now the challenge is how do I sample from these 2 polynomials, these piecewise polynomials in an efficient manner. So what we need to do now is a bit different to what we had to do before. So if I rub off some of this stuff and try and explain the changes. So we need 2 new things. We need a new block encoding, and we need a new way of applying our polynomial transformations. What we had before was a block encoding with diagonal values starting at 1 and going to -1 across that. So these are the diagonal values along the y-axis, and it looks something like this. And what we want now is something where we split up our range into S different regions. So S regions. And in each of those regions, it ranges from 1 to -1. So this is like region 0, region 1, region 2. And these regions don't have to be the same size, but it is important to range from 1 to -1 in each region, because we have this condition here that the polynomial has to be bounded across the whole range. And we're fixing these polynomials to amplitudes. So the amplitudes will be bounded across the whole range. So it just makes our lives easier if the domain of the that we're fitting across is the whole range from 1 to -1, because then if we have a well-behaved polynomial, it won't that isn't oscillating wildly, it won't exceed those bounds in that range. And then for each of these S regions, we then have to apply a different polynomial. So to this region, we're going to apply P0, to this one P1, to this region P2. The other thing to bear in mind is that we have a width to each of these regions that I'll refer to as capital L0 or 2 to the little l of 0. But there's a restriction in the algorithm that the size of the regions has to be a power of 2. And I'll explain where that comes from in a bit. So at the end of doing all of this, we'll end up with a block encoding that looks more like this compared to what we had before, where we have a different polynomial applied to different sized regions where the whole range of the whole domain is included. And then we can do the same tricks before applying to uniform superposition, and we get what we desire. But first, I'll explain how we get the block encoding and then how we do the different polynomials. So this is the circuit that gives you the piecewise linear diagonal block encoding. And I'll go through it in detail to justify that it actually does what I say it does, because it's a bit of a mouthful to take in at once. I'm somewhat cheating here because I'm hiding a lot of the complexity in this CC operator that I haven't defined. It is defined in the paper. And what it effectively is doing is a high bit carry operation. So it's adding the L least significant bits of K, the L least significant bits of X. And if that would result in a carry bit, then it adds 1. And you can do this in an efficient manner. But I'll just demonstrate that this block encoding actually produces the matrix that we want. So in order for it to block encoding, the flags have to start. So this will be the flag. This is the flags to start in 0. Well, actually this is from the right because of the confusing notations that I'm coming from the right, but this is in the diagram but left on the board. And some X prime, and then the flags again have to be in 0 and then as an X. These slashes with a line through them mean just a controlled rotation, just controlled. So the X's are just going to go straight through. We can just forget about this. So U is already going to be diagonal because we're just controlling off that. Now we can look at what happens to the flag qubits. So from the right, we apply a bunch of Hamieds to the flags. And so we get a uniform superposition over L max. There we go. And then the same thing happens on the left. And because it's just controlled off these are just going to, and these are orthogonal states. We're only going to have these contributing where K is equal to K prime. So in the end, this just gives us a 1 over L max sum over K equals 0 to L max contribution. The interesting stuff happens with the flag qubit. So from the right-hand side, if I'm drawing the line here, the right-hand side, we get the minus state coming in. So you can write the minus state like this. And then from the left-hand side, we have this high bit add. I've ignored the control line for this because it doesn't have an impact, but you have this high bit add where KLSX is equal to the least significant bits of K. And so this is just a sum over 0. That should be A square root 2. And then what I've written up on the board already. So here the LSX is denoting how wide the region that the element X is in is, if that makes sense, how many qubits you need to represent it. And so that's what that sort of cheating notation is. Yeah. So now we have this. We can simplify the left-hand side because K only ever appears as KLSX. So we only actually need to sum over the range of the least significant bits, the LSX least significant bits. So we could write that as Lmax, and then Lmax. Yeah, sorry. Yeah. Just Lmax over LSX times doing just summing to. There should be a -1 there. And then we can look at this range of numbers. So this is a range of K from 0 to LSX. And if we split this range here such that the width of this region is equal in length to the LSX least significant bits of X, then we can see that this here, which is either 0 or 1, in this region where K plus XLSX is greater than 2 to the LSX, this is going to be 1. And in this region where it is less than that, is going to be 0. So now I can split my summation here into 2 parts. So, yeah, I'll just get that lower. So my first summation is to LSX minus X. LSX, sorry for the shoddy notation. And then we have the sum over AB, what's inside, B over 2A plus 0. And then we have the other term where we start the summation where this one left off. So that should be a -1 then. LSX minus X, LSX up to the end. And now we have the same thing in the side of the summation as before, but there's a +1. And we can actually easily see what these evaluate to. This here, B, is same as A, so -1 to the AB. Summed over is just going to give us +1. There should be a plus then. And then there should be a plus. Yeah, and then this should be a -1. And therefore, this is just going to be the number of elements here, which we've already figured out from there. And it's just going to be minus the number of elements here, which is that. So in the end, we just get exactly what we wanted, which is LSX. I won't try and say it out loud. This is from the first term minus second term. And then that gives us exactly what we have on the board, which is this ranging from 1 to -1 in each region. And so, yeah, that's my justification that this does produce the correct block encoding. And it's cheap. So the cost to do this only scales linearly in the number of regions and linearly, logarithmically in the length of the largest region. So it's very cheap to do this block encoding.
Painful is CC again.
CC is an add. It's yeah. So it's but I have it at the end, doesn't she?
So it involves the largest number of
yeah. So
blocks. And then
yeah. So I'll show you the add. It looks like this, right? So I mean, we don't have these, but we just do a unit iteration off the X line. So we calculate all the carry bits. Then we control which carry bit we actually want to copy up. Then we undo. So it's actually just it costs just a single add to do this CC.
So computing carries is like a modified addition.
Yeah, it's a modified addition. Yeah. Where are we? Here. So it's actually very cheap to do this implementation. So now we have our block encoding, we have to apply a different polynomial to each section of it. And as I mentioned earlier, the polynomial is entirely specified by the face factor. So if I could apply a different phase factor to each section of my block encoding, I would apply a different polynomial to each section of my block encoding. So I have to control off the X register and apply a different phase factor depending on which section X is in. But the naive approach to doing this is going to be really inefficient, because if I want to control off every possible value of X, then I'm going to need to do linear iteration over 2 to the n different values, and now I've not gained anything at all. But luckily, there's this sort of magic ingredient, which is called variable linear iteration, which is where instead, when I do my linear iteration through X, so instead of iterating over each individual element, I can ignore bits at a time, and then I can apply the same operation to a range of bits that have the same most significant values, if that makes sense. So here, you can sort of see what I mean. I've split it up into 4 sections rather than 8. And the first 2 sections are use all the bits. The next section, I ignore the last bit, and so it's of size 2. The next section, I ignore the last 2 bits, so it's of size 4. Now, the restriction on this is that the segments have to be of size power of 2, and they have to start at a multiple of that power of 2, because they have to all start at 0 and all end at 1. And carrying out this variable linear iteration, instead of costing 2 to the n, it costs in the number of sections that I have. So I only have to iterate over s different regions, and in each of those regions, I have to apply 1 controlled rotation, which costs me 2 normal rotation gates. And I have to do this because I'm doing this indefinite parity version. I actually have to do 2 d phase gates rather than d phase gates, which gives me this total of 4 ds rotation gates. So going forwards, the magic cost to think of, what we should think of costing this approach as using is sort of ds, the degree of the polynomial, the maximum degree of the polynomial times the number of sections of the polynomial is how the cost of this algorithm scales.
So in this, let's say you wanted them all to be the same length.
Yeah.
All the sections.
If you want them all to be the same length, you can do some tricks actually where you don't have to do that.
Certainly make something, okay, fine.
Yeah.
But if you wanted them mostly to be the same length and then some to be smaller, you can group the smaller things together so they have the same polynomial.
Yeah.
You're limited by the half of the total size of your space, effectively. Something has to be half.
So I mean, this approach works very well for some of the things I'll mention later, where you have like an exponentially shrinking region as you approach singularity. But you're right, like if I have a point where I want to use a very small region, as I approach that point, I have to shrink down my regions as I get there. I can't just I can jump straight down, but on the other side, I will then have to go back up again, if that makes sense. Yeah. So
but you can have multiple regions of the same length.
Yeah.
So
Yeah.
it's only that they have to be sequentially, they have to be going up or down.
Yeah. And I mean, this is how variable linear iteration works. So this is normal linear iteration here, where I've made sure that my first at this point x is definitely 0. At this point x is definitely 1, and so on and so forth. And then if I just don't go all the way down the tree, at this point x is either 4 or 5, and at this point x is either 12 to 15.
Yes, so stopping yourself on the first qubit.
Exactly.
First bit, basically.
Yeah, exactly. And so that this is much cheaper to do. And then we wouldn't be doing CNOPS off it, we'd be doing controlled rotations, but I just stole this from the original paper. So yeah, that's effectively all you need. This is the circuit that will do piecewise QSVT on your linear diagonal block encoding with a cost of DS gates. Does anyone have any more questions about that before I move on to the applications? The number of qubits? Yeah, so to do this, as you can see here, to do this linear iteration, I do need some ancillas. We didn't do much costing in terms of, so it's not that expensive a number of qubits, it's sort of linear, but we didn't focus too much on the number of qubits because this is a state preparation technique. It is sort of assumes that whatever algorithm will come after it will use more qubits, and therefore you have a lot of extra qubits spare when you're doing a state preparation, if that makes sense.
Because you're always putting it back where they want. So you're
Yeah.
Can
Okay.
I ask a question?
Yeah.
Sorry, can I ask
No, go
a
for it.
quick No, sorry, thanks. Yeah, I'm just wondering about the classical overhead here. So, you know, as you rightly said at the start, there's an exponential number of these of coefficients for in general for these state vectors, and then you say so you want to piecewise so you want to kind of get these piecewise polynomials and then fit along each of the kind of domains, fit the polynomial to get these to get an approximation to the coefficients. But I'm wondering, do you not need an exponential number of these polynomials in general, or is it that you're is it that you always know that the number of these domains will be less than exponential, or will be such that the because naively I thought that you would have to fit an exponential number of these polynomials, and assuming that's done classically, then that means an exponential classical overhead. But I guess it's better than that.
So the this won't approximate arbitrary state. So this is only going to be useful for states that admit low degree piecewise polynomial approximations. So you're completely right. Like if I wanted to do an arbitrary quantum state, like you gave me some arbitrary noisy data and I had to fit polynomials to it, then well my polynomials aren't going to be low degree either. So I'm going to need to use like for n points an n-1 degree polynomial, and then I've not gained anything because this d will be, you know, 2 to the n or whatever, you know, however I split up my regions. I might get a potentially a quadratic improvement, but that's not good enough. So like yeah, definitely. So the examples I'm about to give is some examples where you do get a good polynomial approximation. In terms of doing this on generic data, we have a generic algorithm which will produce for a given maximum degree the optimal polynomial approximation. And you can do this because each of these regions sits inside, it strictly sits inside larger regions. I can sort of check the larger regions first and see if I have a d degree polynomial that fits that region. Then if it doesn't, I look at the 2 regions inside it and try again, and then try again. And so this is, you know, it's a greedy algorithm, but it will then find you the, you know, given error tolerance and a given degree, you will find the like optimal splitting of your polynomial into regions.
I see.
Like the smallest number of regions.
I see. I see. So I guess this will maybe this will be answered in your upcoming applications. But then I'm wondering what kind of is there any intuition on what kind of states have that property, or as you say, states that must admit a low degree polynomial approximation of the coefficients. Yeah. Then I wonder, okay, physically, do we have any intuition for what those states would be? But yeah, sorry, I should probably just wait for your application.
No, it's fine. Most of the states I imagine that will be most easily approximated like this are ones that are derived from some sort of analytic root rather than necessarily noisy data, or from some data phenomenon that has some sort of structure to it. I think if there's no structure in your data, that no hope of compression. So if that makes sense.
Great. Thanks very much. That's fine. Thank you.
So yeah, so we have a couple of different applications. So I'll just go through them. So the first one is if I wanted, so this is, you know, the graph from before with the amplitudes, and the different colors show the different polynomials fitted onto this. If I wanted to load square root x, using using the original method of a single polynomial, it's explicitly stated in the original paper that this is hard because I can't find a polynomial that gets arbitrarily a single polynomial that's arbitrarily good as you approach 0 because of the singularity. But what we find is that you can do this if you have a piecewise polynomial. So square x looks something like that. And I can't find a single polynomial that goes all the way up to 0. But if I instead I have a finite quantum computer with n qubits, if I split my state up into if I split my region up into regions of size 2 to the minus n, then the next region is double that size, 2 to the minus n plus 1. The next region is double that size, 2 to the n minus n plus 2. Then each of these regions, we can find a very efficient polynomial approximation to it. So you can see this from using Chebyshev polynomials. So there's a theorem that states that if I have, right up here, if I have a function f complex function, and I want to approximate it on the range on the domain -1 to 1, and f is analytic and bounded by m on what we call a Bernstein ellipse, which is an ellipse around centered at 0 with width with semi-major axis given by rho plus rho minus 1 and semi-minor axis given by rho minus 1 over 2. If it's analytic and bounded in this region, then the Chebyshev polynomials of degree d will be within 2m over rho minus 1 rho minus d of the function f on this range -1 to 1. So we can apply this logic back to our square root x, and I can draw a Bernstein ellipse which has this tip at 0 for each of these regions. So there'll be one like this, one like this, one like this. And when we rescale the region so that it goes from -1 to 1, we find the row for each of these regions is exactly the same. And that row is 3 plus square root of 8. And so you get this exponentially good polynomial approximation to these exponentially shrinking regions. And so therefore, I only need to use a degree which is logarithmic in my accuracy that I want. And I've used n regions, so I only need n log 1 over epsilon rotation gates, or n log 1 over epsilon squared t gates. And this is exponentially better than doing it naively, where I would have needed 2 to the n rotation gates in order to load it. So don't necessarily know why you'd want to load square root x, but it's because if they said that they couldn't do it. You can do a similar trick for log x. I won't go through it. You can do it using Chebyshev, but you can also do it using Taylor series, and you have to split your regions that you do here twice again, and you also have to take account for the fact that when I normalize the log function, as I take a finer and finer grading towards 0, it's larger and larger renormalization by a factor of n. So I have this extra n in the amplitude amplification cost. So it's n squared rather than n. So you have to be careful with this amplitude amplification cost. If I have a function whereby taking a finer and finer grading doesn't increase the maximum value, and it's like a nice continuous function on that interval, then I don't have an increasing amplitude amplification cost. But here, because the normalized maximum value is increasing, I have to pay that cost. This is why you couldn't approximate the delta function arbitrarily close if you do this, because you know, it
So
normalize.
what do you in this figure?
So here, what degree did I use to do this?
Yeah,
I can't remember.
Yeah, just to get a feel of how
Probably like 4 or 3. You know,
they're not high order.
no. Yeah, it would have been a low degree polynomial. It's actually very straight in the section, so that,
Yeah, well, it's great to make it shorter.
exactly. Well, this is also only up to 128.
Yeah.
You know, basis elements.
1 over r, or 1 over x.
Yeah.
Yeah. So 1 over x you can do, but there isn't as we do have some proofs like, but it doesn't give you particularly nice results, like not as neat as these, because of this renormalization problem.
Okay, so you have to get it bounded between.
Yeah. So, and then because you have to bound it, you end up with actually doing 1 over x on an arbitrary region, as you're sort of doing the same function every single time.
So.
Oh, yeah.
Yeah, exactly.
Yeah, so
Yeah.
poles, so here you've got singularities,
Mhm.
you've got rather than a pole. So a pole is always going to be much more difficult to model in this setting.
Yeah. But also, if you have a pole like 1 over x, it's sort of just a rescaling of your vectors to start with. So yeah. And
Over x squared was. That's been the same thing.
yeah, no, so I mean, I can't remember. We did have some results on the higher order poles, and I'm pretty sure for 1 over x we had a bound. For the higher order poles, we struggled because you ended up in some area of complexity, complex analysis where people just hadn't produced a result, and we weren't going to produce. we weren't going to just churn out a brand new like bounding of poles. Yeah, so the most exciting application though I think is this B-spline window. So why do we care about B-spline window? Well, what B-spline window is it's a function from classical signal processing theory, and it's the self-convolution of the rectangle function. So the first one is just a straight line. The second one is two linear lines. It's a triangle. Then it looks a bit more like this, and then this is like the eighth one. And sort of see it looks a bit like a Gaussian, but it's fundamentally different. And the property that makes it nice is that in the Fourier domain, it's very tightly peaked. So this is its expression in the Fourier domain. And this has a very sharp peak. And the reason that's useful is because I can use it to boost quantum phase estimation. So I'll quickly explain how you do that. So quantum phase estimation in its naive form is only good if your energies, so we start with some psi here, and then in normal quantum phase estimation, we apply Hamieds to each of our ancillas, and then we control off the ancilla onto u squared, u cubed, etc. And then here we apply inverse quantum Fourier transform, and then we get our energies out here. That's quantum phase estimation. And this only works well if the energy nicely fits onto this binary, it's nicely expressed in binary of this resolution. Because what you look at when you look at the states that we have here, we have a sum over 1 over square root of n x. This comes from our distribution before. Then we applied this, and we got e to the IEX sign, picking up the energy. And now when we apply inverse quantum Fourier transform, we want, if this exactly matched on, would get the E would come down. What actually happens if it doesn't exactly match is we end up with something that looks a bit more like the sinc. Well, it's not exactly the sinc function. It's like, I mean, I can write it. Could write it exactly. Sine of like pi x minus e over sine of pi over n x minus e of x psi. And this is peaked around e, but it's not sharply peaked. So it has fat tails. So the probability of measuring an energy that isn't close to the actual energy is large. And this causes problems when we want to do coherent quantum phase estimation. But there's a nice trick whereby instead of initializing my state up here as Hamieds, if I initialize it with some w of x, not written that very well, some w of x, then here instead of 1 over square root of n, I have w of x. And then when I do quantum Fourier transform with this, this is something multiplied by a phase. And when I do a Fourier transform, that's equivalent to doing a shift after doing the Fourier transform. So what I have down here, and I mean, it doesn't work, it's a little bit worse than this, but you effectively get w, the Fourier transform of w shifted by e. So by this logic, if we prepare the B-spline window function on the ancillas and then do phase estimation, at the end we will get an energy distribution distributed according to the Fourier transform of the B-spline function, which is sharply peaked. And now the probability of measuring in the tails is much lower. So this is an existing technique, and it's mainly used with the Kaiser window, which is thought to be the nearly optimal approach for this. There's the actual optimal would be something called DPSS, but it's much harder to. And in classical signal processing, I don't think they even use. I think they use the Kaiser window because it's such a good approximation. But what we found is that this B-spline window has the same asymptotic scaling of tail probability as the Kaiser window. So it's not as good, but it's almost as good. And so you can see that here. So on the right hand side, we can see the tail probability here and the number of additional ancillas that you've needed to use to get the tail probability down, depending on the window. So the top line is our sort of control. That's if you don't use a window function. That's if you just use Hamied. Then if you use the B-spline window or the Kaiser window, you get this log scaling in number of additional ancillas you need to get the tail probability down. And as you can see here, even with just 4 additional ancillas, and the nice thing about this is these are really additional. So no matter how large my phase estimation register was before I started adding the window function, I only ever have to add this number of additional ancillas. It really isn't an additional number. And even for 4, the Kaiser window's got a tail probability of 10 to the minus 20. And the B-spline window has a tail probability of 10 to the minus like 13. And it's like on realistic quantum devices, we're never going to be, well, we might, one day we can hope to see measurement likelihoods of that. But in reality, we're not going to. So my argument is that you don't lose much, at least on anything near term, to use the B-spline function over the Kaiser function, even when you've gone to modest numbers of qubits. But you do gain a lot in terms of preparation cost. So here we're comparing the cost of preparing the B-spline window to the cost of preparing the Kaiser window using the state of the art for the Kaiser window, which is actually to do the Taylor series expansion and do a single polynomial approximation. And it's almost 100 times cheaper to do the B-spline window in terms of T-gates when you use 4 additional ancillas. So I think that there's potentially a big saving to be made there when you're boosting QPE to use the B-spline window and this piecewise polynomial preparation technique. So I think that's the most exciting application for it. And yeah, that's about it. So the main takeaway is that if you have a low degree piecewise polynomial, you can load it in the degree times number of regions rotation gates. And there's a couple of efficient examples. And yeah, that's it. So any questions, I'm very happy to take them. Yes.
This is like, that's been factored into.
Yeah, into these costs. Yeah.
And you've used in fact, know something about the juggling, right? So give you the optimal amplitude amplification.
No, you don't need to use that. So the amplitude amplification, all you need to do is reflect off the flag qubits being all 0 state.
But the number of times you need
to do that is to do with the normalization of this polynomial, like how much I need to renormalize it by to fit it into my block encoding. And that scales badly if my polynomial is like, the further away from a flat distribution, the worse it gets. And so if I have a delta function, that's the worst it gets. Then I have an amplitude amplification cost of square it. But if I have a nicely behaved function, like a function which just, I can draw on a piece of paper, and then increasing the number of qubits corresponds to taking a finer grading of this function. In that case, I don't have an amplitude amplification cost that scales with the number of qubits. It tends towards a fixed constant, which is the filling fraction. So the amplitude amplification cost is effectively the inverse filling fraction of my function. Yeah.
The number of derivatives that you have to do, you know already.
Yeah.
It's not something you have to find with phase estimation.
No, you know that normalization of your status. Yeah.
I suppose because you know that you're trying to compute something, you know everything about what you're trying to compute.
To do.
So it's a bit easier that way.
Yeah.
Yes.
Yeah. But the other important caveat to this is that you can't do piecewise QSVT to just in general. This only we can do it because we're doing it to this linear diagonal block encoding that has this particular structure. If I wanted to do apply an arbitrary piecewise polynomial to an arbitrary block encoding, then I would have to do some sort of controlling. I'd have to do some sort of controlling off the singular values themselves rather than off we just have the coincidence between the singular values and the computational basis, which you don't always have. That makes sense.
Unless you could transform it such that.
Yeah, if you could. Yeah, exactly. So if you use another QSVT algorithm to do some sort of thresholding, then you could do, yeah. But yeah.
Yeah, a question about three gates.
Mhm.
Didn't you have been sharing costs or I don't know what three gates means. So I was curious about how do you do these things?
Used Qualtron, which is the new Google library. Yeah, yeah. And so I don't have access to that code anymore. And since the new stuff about the T gates and C-naughts potentially becoming more important, I would like to rerun it and find out what the C-naught costing was. But because Qualtron has that integrated anyway, that we should have the costs just.
Anyone online? Questions? Okay, thanks very much.
Thank you very much for having me.
Yes.
There's my laptop.
How about distance? What is A and B? What was A and B in this bit on the left?
Oh,
Go quite
this,
fast at this.
I did. I'm sorry. Yeah.
It's like-
It's the summation. So B, for example, here, this is the minus state. This is just another way of writing the minus state in terms of the computational basis elements, right? Like, so for the zero, this is zero plus. Wait, where's the thing?
Oh, so B was
Here's a pen.
the computational basis.
This is just zero minus one over the square root.
Yeah, okay.
Yeah.
Oh, okay. Yeah.
And
B is a computational basis then.
Yeah.
Yeah, okay. Yeah.
Definitely some bit, but yeah.
And then, but then when we, yeah, okay. I think it just not makes sense. Ignore me, I'm just.